Hello students, this is your physics teacher Sandeep Tiwari. Now we will study energy stored in a capacitor. So in the figure to the left side I have shown a capacitor which is blank, and after that I have shown a capacitor which has been charged and the charge on it is Q dash on the positive plate and minus Q dash on the negative plate. And at the right end I have shown a completely charged capacitor with charges Q and minus Q on the plates. Now as we are charging the capacitor, the charge is flowing from one side to the other. Okay, so if delta Q dash charge is moving to the positive plate, so the charge there will become Q dash plus delta Q dash, and on the negative plate it will become minus Q dash minus delta Q dash. So while this charge is transferring, work is being done. The work is being done because there is a potential difference between the two plates. So if charge delta Q dash is moving and V dash is the potential difference between the plates, then the work done is delta W is equal to V dash delta Q dash. Work is equal to potential difference multiplied by the charge that is transferred. So in this way, every time the charge is transferring from one plate to another, work is being done. So to find the total work done, we will integrate this expression. So the small work delta W is equal to V dash delta Q dash. In place of V dash we are keeping Q dash over C. We know that the potential difference is charge divided by the capacitance. Now integrating, the work will be integration of delta W, that is integration of Q dash by C delta Q dash, and the limits will be 0 to Q because the charge initially will be 0 and finally it will become capital Q. So when we integrate, we will get the work as Q square upon 2C. Now we can put the value of Q as Cv, so we will get the work as C square V square upon 2C, or half Cv square. Now we can write Cv as Q. We can take 1C and 1V and we can write it as Q. Then we will get the expression W is equal to QV by 2. What we have done, that in the half Cv square expression we have taken 1C and 1V and we have written as Q. So we are getting the expression W is equal to QV by 2. Now the work that is being done will get stored as potential energy in the capacitor. So we will write that this work is equal to U. U is the symbol for potential energy. So we will say that the potential energy U is half Cv square or Q square upon 2C or QV by 2. So this is the expression for the potential energy of a capacitor. Now we have this energy is the electrostatic potential energy. Now energy per unit volume, this is also a very important expression, like we write it as U bar. Okay, we know the total energy but we want to get the energy per unit volume. So that will be the total energy half Cv square. This is the total energy and we will divide it by the volume. This is the energy per unit volume. So half Cv square is there. Volume will be area into distance between the plates. Plate area multiplied by the separation. It will be a cubical volume. So if we are having a parallel plate capacitor, then it is a cuboid or cubical, you can say. So the area of the plates multiplied by the gap between the plates. So we will get half. Now I am keeping the value of C here. C is the capacitance of the parallel plate capacitor, that is A epsilon naught over D. So the value of C has been kept here. A into D is already there, V square is already there. So A is cancelling A. So we get this half epsilon naught V by D whole square. Now this V by D, we can say it is the electric field. Electric field is potential difference divided by the distance between the plates. So we get U bar is equal to half epsilon naught E square. This is the energy density as well. We call it energy density as well. Energy per unit volume or energy density. So this is the formula for energy density inside a charged capacitor when the electric field between the plates is E. Epsilon is the permittivity of the free space. Free space means air, vacuum. Okay. So this is the formula for energy density.